For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@mathsassignmenthelp.com, info@mathsassignmenthelp.com, or reach us at https://www.mathsassignmenthelp.com.
New visitor.
Problem 1. Let L and M be finite-dimensional linear spaces and let F, L, M be a linear map. Prove that the subspaces Ker F and IMF are finite-dimensional and dim Ker F plus dim IMF equals dim L. Hint: use the extension of a basis theorem. Problem 2. Consider the space L, V, of linear maps from a finite-dimensional real linear space V to itself. Which of the following subsets of L, V are linear spaces? A. F is an element of L, V, dim IMF equals 0. B. F is an element of L, V, dim kerf equals 0. C. F is an element of L, V, dim IMF dim V. Reformulate the obtained results in terms of matrices. mathsassignmenthelp.com. Problem 3. A. Show that there are no finite square real or complex matrices X and Y such that XY minus YX equals I, where I is the identity matrix. D. B. Check that multiplication by X and differentiation are linear dx maps on the real or complex space P of all polynomials in 1D variable X. Compute the action of dxx minus X in P. Here dx denotes the composition of two maps. C. Introduce the concept of a matrix with infinitely many rows and columns. Define the multiplication for infinite matrices in which each column and each row has a finite number of non-zero elements. Using B, find a solution for xy minus yx equals I in terms of infinite matrices. mathsassignmenthelp.com. Solution 1. Let L and M be finite-dimensional linear spaces and let F, L, M be a linear map. We want to show that IMF and Ker F are finite-dimensional and that dim IMF plus dim kerf equals dim L. We assume that dim L equals N. Let Bj be a basis for kernel of F. By the basis extension theorem, we know that there are linearly independent vectors, Ck, such that the ordered set Ai equals Bj Ck forms a basis for L. Since the total number of basis elements for L is finite, it must be that Ker F subset of or equal to L is also finite dimensional. Thus, dim Ker F equals L less than or equal to N. Next we show that F, Ai, N span IMF. We choose V is an element of IMF. Since I equals L plus 1 N Ai spans L, there exist scalars D such that V equals F, di. Noting that I equals 1 F, Ai equals 0, 1 less than or equal to I less than or equal to L, we have V equals IN equals L plus 1 CIF, Ai. Thus, F, Ai, IN equals L plus 1 spans IMF. F. To verify the linear independence of F, Ai, N, we consider the linear Ni equals L plus 1 in combination I equals L plus 1 CIF, Ai equals 0. Then by linearity Fi equals L plus 1 Ci equals 0. Since Ai are linearly independent, it must be that all Ci equals 0. Hence all N, F, Ai, I equals L plus 1 are linearly independent and we can consider them a basis for IMF. This also confirms that IMF is finite dimensional. Hence, dim IMF plus dim kerf equals dim L. mathsassignmenthelp.com. Solution 2. A. F is an element of L, V, dim IMF equals 0. This is a subspace. The defining condition of this subset is equivalent to F equals 0. Thus, for all V is an element of V, F, V equals 0. By linearity, this is also true for any combination of such linear maps. Considering the matrix representation of this subspace of linear maps, we conclude that it is isomorphic to the subspace of zero matrices. B, F is an element of L, V, dim kerf equals 0. This is not a subspace, unless dim V equals 0. We prove this by contradiction. Suppose V is an element of V. Then necessarily for F in the subset, F, V equals 0. Further, by linearity it must be that Kf, V equals 0, K is an element of F. We pick K equals 0 and then for any vector V is an element of V, the action of Kf on V gives 0, independent of V. Thus dim ker Kf equals 0. However, if dim V equals 0 then also dim ker F equals 0. In this case V subset of or equal to 0, and necessarily F equals 0. Formulated in terms of matrices, we can consider this subset of linear transforms isomorphic with the set of matrices with rank equal to the dimension of V. This is not a subspace since multiplication of any such matrix by 0 will result in a matrix that has rank less than the dimension of V unless the dimension of V is 0. mathsassignmenthelp.com. C. F is an element of L, V, dim IMF dim V. This is not a subspace, unless dim V equals 1. We prove this by contradiction. Let dim V greater than or equal to 2 and let I equals 1 be a basis for V. Further, let phi aj, for I equals j and phi aj 0, for I equals j. Then for thus, dim imphi equals 1 dim V equals ni equals 1 ci phi V equals ci V equals. However, nn phi V equals V and dim im phi equals n equals dim V. For dim V equals 1 I equals 1 I equals 1 it must be that F equals 0, dim IMF equals 0 and proof follows as in part A. We cannot have dim V equals 0, since then dim IMF equals dim V. We can consider this subset of linear transforms isomorphic to the set of matrices with rank less than the dimension of V. For dim V greater than 1 we consider a subset of such linearly independent matrices of rank 1 and note that the sum of these matrices may result in a matrix of rank dim V. In case dim V equals 1 our subset is a subspace of zero matrices as described in part A. Solution 3. We want to prove that there are no finite square matrices such that xy minus yx equals I. By contradiction, suppose we could find such x and y. Let x, y, I is an element of fm times m. Then trace xy minus yx equals trace I equals m. However, mathsassignmenthelp.com. Thus, it is impossible to find finite square matrices that satisfy xy minus yx equals I. Both of these maps are linear.